Hi everybody and welcome back to Electrified Veronika, where we're talking about electric vehicle and battery technology. I am in Las Vegas at CES 2023. CES is the largest consumer electronics show in the world, and it has a significantly growing electrification area. Today, we're taking a deep dive into what I would call the brain of the battery management system. If you get into your electric car and you're looking at the state of charge and the remaining range, have you ever wondered where this number actually comes from? Well, it can't be directly measured, and a lot of it comes back to the BMS. One of the leading edge companies developing BMS solutions is Texas Instruments, and I'm really excited to talk to them about their latest product launch. Let's go!
Hey Veronika, how are you?
Very nice to meet you. Good, how are you?
I'm doing very well, thank you.
Thank you for showing me around. Let's start with the basics. What is the role of a battery management system in an electric car?
Sure, that's a great question. So as you know, the battery management system is really the core of an electric vehicle. It could be a 400 volt or an 800 volt system. That means there could be 100 or even 200 lithium-ion cells that are located inside the battery pack. So really the battery management system is a sentinel, if you will, a watchdog, as well as a caretaker for the system. So by that I mean you always have to continuously monitor the battery cells. You need to report those voltages, the temperatures, as well as the pack currents to the overall system so that we can, at the end of the day, calculate how much range is left in your vehicle. But at the same time, lithium-ion cells are quite volatile in nature, and you always have to take care of them. We need to make sure that they're healthy. And so it needs to provide overall safety for the system. And so in addition to monitoring the voltages, currents, and temperatures, we also have to do other things like perform isolation resistance monitoring, or control the contactors, or to control pyro elements, to disconnect the battery from the inverter, for example, when there's a critical situation like a car crash or a thermal runaway event, and so on.
So the battery is also the most expensive single component in an electric car, so it's really important to keep it healthy over lifetime.
That's correct.
Where is it actually located in the EV?
Yeah, so we actually have a model car here. It's a toy car, but just as a demonstrator purpose. The battery management system is typically going to be located on the underside of a vehicle. And so if you imagine you're sitting in a car, underneath your seat, on the entire floor bed of the vehicle would be the battery pack.
A high-voltage battery pack in an electric car is typically located underneath the floor. It consists of several individual battery modules, which themselves consist of individual battery cells. Now, each of those battery cells has a certain operation window in which they feel safe, they operate reliable over lifetime. There is a certain minimum and maximum voltage that should not be exceeded, otherwise you overcharge or over-discharge the battery, which can lead to severe safety issues. And the same is true for minimum and maximum charge and discharge currents, as well as a certain temperature range that this battery is safe and comfortable to operate at. And now one major role of the BMS is maintaining these healthy and safe limits over lifetime. The voltage, current, and temperature limits for a safe operation are different for different battery chemistries, basically depending on the anode and the cathode material chosen. While the most popular anode material today is graphite, for the cathode side, the two most popular chemistries are LFP, which is lithium iron phosphate, and NMC, which is lithium nickel manganese cobalt oxide. And different material pairings of anode and cathode provide different voltage levels in battery cells. This is an example for an NMC cathode chemistry where typical voltages range from 2.5 to 4.2 volts. Importantly now, pretty much every car manufacturer has their own battery design, using various battery cells, formats, chemistries, different cooling systems, modules, and pack designs. So there is no one BMS fits all approach. So a BMS architecture really needs to be designed, it needs to be developed, it needs to be calibrated for every new battery design.
So how does the BMS actually look like? Can we look at one?
Sure, we've got one right here. Let's take a look at it. So let's go take a look at here. This is our battery management system development kit.
So this entire system here is the BMS.
Yeah.
I can see a lot of green circuit boards. For somebody that is looking at this for the first time, what do we see here? What are the individual parts of the BMS?
Sure, let's take a high-level view first, and maybe we can dig into the actual details of the system. So in a battery management system, there are essentially three main subsystems. There is the brain of the battery management system, which is called the battery management unit. And then that's where the main safety microcontroller is sitting. That's what's controlling every other subsystem inside the BMS.
Where do we see that here?
That would be located here. So you can see this red board, that's our MCU, the safety MCU, which is running AUTOSAR and running all the software and hardware. And so that's the brain. And there is a second subsystem, which would be called the Cell Supervisor Unit. And that's an acronym, it would be a CSU. And that is where we perform battery monitoring as well as cell balancing. And that's basically looking at all of the lithium-ion cells and performing that monitoring function of it. And we see that here on the upper corner. There's, for demonstration purposes, this is a wired system currently. And yeah, we have two of the CSUs that are connected together, and they're connected to real cells.
Okay, so those wires here, we can imagine that these are the wires coming from the individual cells.
Yes.
So we get the cell voltages in and the temperatures, and this is read by this part here.
Correct, and that would be sent over again from the Cell Supervisor Unit over to the Battery Management Unit. Okay. Now there is the third and final subsystem, which is kind of the intelligent battery junction box, if you will. This is the part which is responsible for the control of the contactors and maybe the control of high voltage relays, pyro elements, but it's also responsible for sensing things like the pack currents as well as pack voltages. And so for that, we have this board here, and that's where we feature our marquee device. It's a pack monitor, and it works in conjunction with our battery monitor. They're kind of a chipset that work together. It monitors the current, and which also comes from the input here. So we actually have a shunt, which we are monitoring for things like overcurrent and so on. And we're measuring high voltage and looking at things like isolation voltages and so on.
Okay, so that's the three main parts of a battery management system. Now, TI is a semiconductor company, right? How many chips are we looking at here, roughly?
That's an interesting question, right? So if I took a guess, I would say probably in a real BMS system, remember, we're going to have more cell supervisor units. I would say there's easily over 100 components in a battery management system alone. The interesting thing here, Veronika, if you look at this, every single black chip that you see on here is a TI device. And that's something that's very unique to TI, because not only are we doing the battery monitoring, we are doing everything ranging from the safety microcontroller to the battery monitor, to the pack monitoring, to contactor control, to pyro element control, all the way down to power, bias power, LDOs, CAN transceivers, and so on. So we really are providing expertise on the entire battery management system. So yeah, there's a lot of components on here, as you can see.
It sounds like the entire ecosystem is covered.
Right.
So a question here. I hear a lot about wireless BMS. Obviously, we have some wires here that are coming from the cells, but what exactly is a wireless BMS?
Right, so this is a wired system. So what we see is the cell voltages coming in, and the cell supervisor units are connected to the battery control unit. You can see the wire that's connected between this board to this board here.
Yes.
Now we also have this system, it's set up as a wireless demonstration unit as well. So taking that same model car, this is actually a real wireless BMS enabled car.
Okay.
So what I have here is the same cell supervisor unit that I have mounted in here. It is mounted here now. And we are monitoring this remote controlled car's battery pack. And we are sending that voltage and current data, voltage and temperature data back over to the MCU wirelessly. And so in our system, we have both wired as well as wireless performance.
Let's talk a little more about the cell supervisor unit. What does it do?
Sure. For that, why don't we take a look at the graphical user interface, which is interfacing to our overall system. So here, we are working with 𝗟𝗏𝗄 as a hardware and loop simulator to provide real cell voltages to our system. And what you can see here is the all voltages being applied to our cell supervisor units. And so the job of the cell supervisor unit is to monitor those voltages. And it must monitor those voltages very accurately, because the more accurately that you can measure the cell voltages, that translates to better overall usage of the battery pack and ultimately better range for the driver.
Let's talk a little bit about what happens actually with these signals. We measure current, voltage, and temperature. What do we do with this?
We have to measure something called state of charge.
If we look at the battery management system in a very simplistic way, we can say that the physically measured quantities, such as voltage, current, and temperature, are input variables which the BMS uses in different algorithms to output quantities such as the state of charge, the state of health, or several status and fault messages. Let's have a closer look at the state of charge. The SOC is an expression of the present battery capacity as a percentage of the maximum capacity. And it is the quantity that finally shows up on your dashboard in your EV together with the electric range. It obviously depends on battery voltage, current, and temperature, but it cannot be measured directly. Common options to estimate or calculate the SOC in a battery are either direct voltage measurement, Coulomb counting, so basically measuring how much charge is going in and out of the battery, or a combination of both. The challenge with determining the SOC solely from voltage measurements becomes clear when looking at the OCV curve of a battery, the open circuit voltage versus the state of charge. You can see that at very low and high state of charge, there is a clear relation between battery voltage and SOC. But as soon as you get into this flat part around 50% state of charge, already very small variations in voltage lead to significant changes in the SOC. This gets even more severe when you change over from an NMC to a LFP chemistry that has an even flatter OCV curve. So overall, very often direct voltage measurements are combined with current measurements and Coulomb counting to get the most accurate SOC.
The accuracy is something that's incredibly important to the system. So the more accurately you're able to measure the cell voltages, in this case, our newest parts are able to measure down to 1 millivolt of accuracy. The better you're able to measure that, the more range that you're going to be able to get out of the battery pack.
Yeah, so we're talking about voltage accuracy, which will affect the accuracy of the state of charge, which will then have an impact on range.
Correct.
Can you elaborate on that a little more?
Well, a lot of this, we have to go back to chemistries, right? Battery chemistries. In the current market, we are moving towards, proliferation of electrical vehicles, and what we'll see is a movement towards lithium iron phosphate battery chemistries. And lithium iron phosphate has a very flat discharge curve, and that means that if in reference to state of charge, when the system's at roughly 20%, for example, 20% to 60%, it's a very flat area. So the more accuracy that I'm able to get, the more I'm able to discern exactly how much percentage state of charge I'm in. If I don't have that accuracy, I won't be able to tell whether I'm at 20% or 60%. But if I have that 1 millivolt of accuracy, I'm able to tell whether I'm at 20%, 22%, or with much higher resolution in essence. And that translates to ultimately better range.
Another role of the BMS is to use all the information it gathers to determine the state of health of the battery. It's often called SOH. It's a measure of how old your battery is and how much capacity it can still hold compared to when it was new. While a new electric car with 100% state of health can drive 400 miles on one charge, an older or used electric car with 80% SOH could only drive 320 miles. If we come back to the corresponding OCV curves, we can see that those curves change as the battery gets older. So the BMS has to know how the curve changes over time to estimate the state of health. And there are different methods to do that, from lookup tables based on battery cell testing to electrothermal and electrochemical modeling to completely data-driven algorithms that take BMS data from several vehicles to estimate SOH and battery lifetime.
You know, sending data to the cloud, sending BMS data, cell data, temperatures, voltages, currents to the cloud, maybe even from several vehicles, and then, you know, connected cars use all this data in big data algorithms, predicting lifetimes and things like this. Can you elaborate a little bit about what happens actually on board of the BMS calculations and algorithms, and what is the trend that you see to sending that to the cloud?
There's a big trend towards, you know, collecting battery pack information. If I have 1 million vehicles on the road, I have a much better understanding if I am able to comprehensively look at how all those batteries are aging. And so there's a big industry trend towards cloud compute, right? So if I'm able to send all of my aging characteristics over the cloud, and then I'm able to do things like machine learning to actually apply, okay, what can I do better? Maybe I can do some self-healing or other kind of extension of health. That will help the industry dramatically, right?
Are car manufacturers doing that today, or is this something for the future?
I think this is something in the very near future, right? There is active, there is activity on this in the market even as we walk around CES here.
I think another important role of the BMS is really keeping the battery safe. What's your thoughts on safety and the battery management system?
So safety is really important. We talked about monitoring of the voltages, the currents, and the temperatures. But in actuality, if we look at that system over there, there's going to be things like contactors. There's going to be pyro elements. There's going to be things that you have to do to make sure the high voltage ground and the low voltage ground are not shorted together so that you electrocute the service technician. So there's a lot of safety things that the BMS has to do, because it's, at the end of the day, a high voltage system, right? And if I have a crash or if I have a over voltage event, I have to disconnect the battery from the load to protect the system. So there's a lot of safety functionalities required here.
I think you had a little demonstration going on here, right?
Yeah, so we're demonstrating one particular portion of the system, which actually is quite fun. We have this remote controlled car, which I'll let you drive, and you can actually crash it into a wall. So while this vehicle is reporting its voltages of the battery pack and the temperatures wirelessly to our main node there, you can drive it around, it's reporting what its signal strength is and all that. You will be able to crash it into a wall, and once you crash, we will fire the pyro element.
Let's try.
Let me give you control of the wheels.
Let's do it.
I heard you're a bit of a lead foot, and you like to drive quite aggressively. Let's take a look at your driving skills.
Where did you hear that?
From your husband. So I'll set the car down.
Okay.
And I want you to drive crazy.
Drive crazy. Okay, I can do that.
I want you to drive. There's going to be an LED which is simulating a pyro fuse. The minute that you crash into a wall, that light will turn on.
Okay.
And it will basically signal that we've fired that pyro element.
So you want me to crash this right into the wall?
Do it.
Are you sure?
Do it.
That's a first.
Do it. All right, so we see the light turning on, right? So we don't actually have a pyro element because it's a one-time element, but we've got driver technologies, SQUIB driver technologies, which actually are able to control and fire these and monitor these pyro fuses. So upon crash in an 800-volt vehicle, disconnect.
Okay, awesome. So we crashed the car. What are we doing next?
Let's take a look at maybe some charging technologies.
Okay.
Yeah,
okay.
So let me take that from you. So TI is actually not only working on electrification of EVs, but we are also working on charging infrastructure, for example. What we're trying to show here is for example, a DC fast charger. And this is basically maybe a vehicle here that we plug into. The latest trends is we have maybe solar or grid infrastructure that we have a lot of energy we want to use to charge our vehicles. And there is something called vehicle to grid or vehicle to home. And here we're showing basically a CCS charger using the latest V2G or V2H protocols that are used in North America and Europe. And we basically can demonstrate multiple technologies, from driving these high voltage relays to driving the lock connection here, to do isolation, to perform wireless communication between all of these DC chargers, right? So maybe you're at a parking lot and you have multiple chargers. They all need to communicate with each other to say, for example, I've only got one car, let's redirect all the power to that one car. So we can use either sub 1 gigahertz technology, 2.4 gigahertz technology, or something that's really, really cool is the latest Matter protocol out there.
Okay, so when I'm going to a charging station and all of a sudden there are more and more EVs coming in and the charging power is reduced, the algorithm behind that is running on here.
Yes, and basically the communication is happening with that wireless protocol that we can support.
That's very interesting. Thank you so much for showing me around, introducing me into what Texas Instruments is doing in the electrification area. To me, chemistry is really the heart of the battery, and the brain of the battery is the BMS. I hope this video gave you a good overview of what the battery management system in an electric car is actually doing. If you have any questions, please leave them down in the comment section. Stay electrified. Bye!